Alright, so with the things we've seen last lesson, we should be able to implement the full tire model in our Matlab Simulink model. Therefore, we had some data available, being this data, the relationship between the slip angle and the lateral force, and the relationship between the longitudinal slip ratio and the longitudinal force. To model these kinds of curves, we had the formula in this form. So our challenge in the last lesson was to define B, C, D and E, but not just fixed values, but we have different curves for different masses of the car or different downwards forces on the tire. So therefore we had to find formulas for B, C, D and E depending on the mass. Well, in fact not for C, because C is fixed at 1.3 for the lateral force and 1.65 for the longitudinal force. In the last course you all obtained formulas for B, D and E for lateral as well as longitudinal situations. However, when I tested these formulas, they were not quite correct. Therefore, I will show you how I determined these formulas that did deliver correct results. So, you can take a look at the graphs I used. When it comes to the lateral force as a function of the slip angle, I see a somewhat constant tangent in the origin for all the curves, independently from the mass. This tangent in the origin seems to be constant and has an angular value of 67.5 degrees. The maximum point is also important, and here you can see the different maximum points that I read from these graphs. Then I've done the same for the relationship between the slip ratio and the longitudinal force. In this case, you can clearly see that you have different tangents in the origin with different angular values: minus 45, minus 65, minus 75, minus 79, and minus 83. Why are these values negative? Well, you can clearly see that the value drops with increasing longitudinal slip ratio. However, the maximum points are at a somewhat constant x value or a constant longitudinal slip ratio value of minus 0.1, or if you look at the other side, plus 0.1. And then I had these different maximum values read from the graph that we got. Now you can wonder how you will implement this information in a relationship between the mass and these values. For instance, if we take a look at the formula, we see that the easiest value to determine is the D value. The D value is purely determined by the peak value of the graphs. And then if we go back one slide, here we have these peak values for different masses, and here we also have these peak values for different masses. I used Matlab to determine the relationship between the X and the Y values, or between the masses and the maximum values D. I will just give an example with random numbers just to show how it works in Matlab. This is my X array. This is my Y array. As I said, random values, they have no relationship to our assignment, but they show how you can easily fit curves in Matlab. Then the only thing we have to do is plot these values against each other. Now we get this plot. We get some lines, but of course the dots do not have to be connected. So we edit the plot and we choose for no line. We do not want a line in between the several data points. We want some kind of marker, let's say a dot, a large dot, that we clearly see the data points like this. Okay, these are the data points. Then we want to do some fitting. Therefore, we have the tools and we have basic fitting tools. And these basic fitting tools are enough for our application. We can choose for a linear relationship, and then you immediately see that this not really is a linear relationship. If I choose for a quadratic relationship, it looks better. A cubic relationship goes through all the points exactly, but maybe that's not necessary, because then we are overfitting data which can be noisy. Why should the data be noisy? Well, if you want to read the values here from the paper, as you can see, these are not exact values, of course. I have drawn some fatty points, and if I take the dimensions here on the paper, I make some mistakes as well. So therefore it might be better to use here a quadratic relationship. And then you can just ask for the equation and you get the equation. Wonderful. This equation is very useful. This method is very useful to do the fitting. And that is how I came to the several values. D is very easy. It's just reading out the peak value. When you know D and you know C as well, and we do know C because it's a fixed value, then you can determine based on this angular value of the tangent, can determine the stiffness B, because we already know C and D. And then the only thing left to determine is the so-called curvature. This so-called curvature depends on B, which we know now already, and C, which is constant, and xm, that's the point at which we observed the maximum value of our curve. Alright, I've just done so. I've done so for B, for the lateral force, and as a function of the mass, then I get this equation, a third order equation. I've already also done so for D with the lateral force. I get this equation, second order. I've done just the same for E, lateral force, again a second order equation. And then of course we can do just the same for the longitudinal force B, which is a third grade equation. The D coefficient for the longitudinal force is just seemingly a perfectly linear equation, and again longitudinal force E coefficient is a third grade equation. Alright, now we seem to have everything. We have these equations. Of course, we have to use the formula here to really describe the force as an output, be it the longitudinal force or the lateral force. So the input will be the longitudinal slip ratio or the slip angle. And of course, we have to determine this kappa and alpha. How to determine that? Well, I made a drawing on the blackboard during the last course to show you how to do it. The kappa value is the difference between the longitudinal speed determined by the vehicle, the wheel, and the actual rotational speed of the wheel multiplied with its radius to have the rotational speed of the wheel at the surface of the tire. This divided by, again, the speed in the x direction at the wheel. This is to determine the kappa value. We also shown how to determine the slip angle. How to determine the slip angle? Well, if we know the speed in the x position, in the x direction, and the speed in the y direction, then we can determine this angular value alpha using a tangent. And for the front wheels, we have to take into account the steering angle delta 1 and delta 2. If we put that all together in our complete model, then we get this. We get this. We start, of course, with our suspension system. Why do we start with the suspension system? Well, because we can determine the downwards force on the tire based on the suspension system. We've done that in the previous courses. We divide that downwards force with G, and we choose to put here a -1. Why is that? Well, as you can see, all these downwards forces are negative. Of course they're negative, they are downwards, but the masses are not described negatively in our graphs for the longitudinal force and the lateral force, so therefore -1 over the gravitational constant G. And we give that as an input being the mass and the mass. For the longitudinal coefficients B, C, D, and E, and the lateral coefficients B, C, D, and E. This is just a matter of implementing the coefficients that I've shown in the previous graphs. You can see here the mass that's on the different wheels. Then we have the longitudinal slip. We have here the dot x values at the wheels. These are the actual values that we obtain. How do we obtain them? Well, we had a certain speed of the center of the car. This is something that will be determined later on in our complete model. If you take a look at the complete model, you see that this will be fed back. We will have these values and we will use feedback to bring them back here. But now we are not that far yet. We are still implementing TireModel, so we just suppose some values to test. These are the values that we suppose, and indeed later on we will determine them exactly and then use a feedback loop to put them here. So we have here the values for dot x at the wheel, dot y at the wheel. We use this for the slip angles and the longitudinal slip, so that's just a matter of implementing this formula and implementing this drawing. As you can see, I also provided an input for delta 1 and delta 2, but I have not connected them yet. However, I can connect them because here I already have delta 1, so I can make this connection and I can make the other connection as well. Play it again. Wait a little bit until the simulation is done. and then you will see these are the values I obtain for the slip angles by applying the correct formulas. These are the values I obtain for the kappa values, obtaining the right formulas. You can see here that I already put a value for the radius of the wheel and the angular rotation of the wheel, and then if we feed that into the magic formula, we get the forces here as a final result. You should obtain the same values for these forces if you give the same inputs to this model. So let's look at the inputs. We have the rotational speed of the wheels, the radius of the wheels, we have the movement of the center of the car in the x direction, the y direction, and the yaw rate of the car, the speed at which the car is turning. We also have the dimensions of the car, AR and AF. We have the B, the distance between the two wheels. Then we have the steering angle. We again have AR plus AF and B, the distance between the two wheels, which goes to the two separate steering angles. We applied a certain standard height for our car. We applied a certain roll, 5 degrees, pitch, 6 degrees, yaw, 14 degrees. Use the roll pitch yaw transformation for the downward force on the wheels, the mass of the wheel multiplied with the gravitational constant. So here we get the height of each corner position of the car. We have the suspension with its downwards forces, the downwards forces which we transform to the masses which are transformed to the coefficients B, C, D and E, and finally these forces should be the result. If you do not obtain that result, you check with your co-students if they obtain that results, what have you done wrong, what have you done differently. If you do not find the answer by comparing your models, then you can always send me an email containing all your models so I can check them. Good luck.